My video report will be on differentiation from first principles. So I already know that given a function f of x, the differential notated as f dash x is equal to dy over dx. And this not only can just be applied to linear, it can also be applied to other powers of x. So we'll start by looking at a quadratic. This could most likely be x squared plus 1, for example. So to get the idea of this and why it doesn't work initially and how we can work on it, let's look at 2 points on this line. So if we were to want this point, which we're just going to call point x, we need to work out the gradient of the tangent at this point. However, if we were just to do the difference in y over the difference in x, in this case, we would actually just work out the gradient of this line, which is clearly wouldn't be the gradient of this line. However, a property that we do know is if we were to work out the gradient of this point to this point, which the difference in x is slightly smaller, the gradient of this line will actually be closer to the gradient of this tangent. And if you follow that pattern, so as difference in x diverges to 0, we should end up with the gradient at point x. So starting on a clean slate, we'll draw a similar graph, f of x, y. And let's start again with point x. And this time we'll actually name this point x plus a certain distance, which in this case will be dx. And this will obviously be dy. And if we were to input this into the function, it can be shown as the function of x. And this one, if we put x plus dx into it, would cause f of x plus d of x. And so, if we were to just try doing the difference in y over the difference in x of this case, so dy would equal f of x plus dx minus f of x to get this distance, so f plus x minus f of x, and difference in x in this case would be x plus dx minus x to get this distance, so x plus dx minus x, which just leaves us with dx. However, if we just did this as it were, difference y over difference x, we again would find out just the gradient of this tangent. However, if we include the property that as difference in x becomes smaller, you will eventually get to the gradient of point x. And this can be shown as f dash x equals setting the limit as difference in x will diverge to 0. And this just means that eventually dx should become 0 at a point, and we will end up with the gradient. But we shouldn't do that yet, as it would completely mess up what we're doing. You'd end up with dx on the point. we'll find out as time goes on why it would mess up. So dy over dx, which is fx plus minus f of x over dx. So that's just dy over dx. In the future will diverge dx to 0. But if we did that now, you just end up with 0 on the bottom, which was what I was trying to get at before. And that won't work yet. And using this, we've now come to our differentiation from first principles formula. And now I will show you an example and how it works. This differentiation from first principles generally works for most functions, including x to the power of fractions or negative fractions. However, I'm going to use x squared as my worked example because it's just a nice simple step-by-step process to show you how that it does work. Yeah, I'll just get started. So, looking at this, first thing that we'll need to work out is f of x plus dx. So f of x plus dx equals, and you do that by looking at the original function and subbing in x plus dx where the x would originally be. So x plus dx, and that x was squared, so now that's squared. And I like to just write what f of x is next to it, just to nice to see them both side by side when putting them into this equation. So now we've done that step, now we just need to sub it in. So f dash x equals 0 of f of x plus dx, which is squared, minus f of x, and f of x is just x squared, all over dx. So now, looking at this, we want to expand what's in the brackets. So dx tends to 0, so we don't forget it. I forgot to add, it's also unsafe to make dx equal to 0 at present because dx is on the bottom, and any fraction with 0 on the bottom just doesn't help us really. So yeah, so we just need to carry on working through it until dx is not on the bottom, and I'll show you how that works out. So carrying on, this expands to x squared plus 2x dx plus dx squared minus x squared, not forgetting that, with dx still on the bottom. Now the x squareds cancel, and as you can see, dx is part of both of these, so dx can cancel with that, leaving us with dx. So now it's safe to let dx tend to 0, as we'll actually still end up with an answer, which f of f dash x now equals, when dx equals 0, just 2x. Yeah, this is what